Okay, so to finish chapter 14 up, we're going to look at the last class of reactions. That we'll call epoxide chemistry. Epoxide chemistry. Okay. So remember what epoxides were?
The blue.
Three-membered rings with an oxygen in there. Do you remember that? Do you remember how to make epoxides? They came from double bonds. Okay. So they came from alkenes. And remember what you reacted with the double bond? A peroxy acid. Okay, so remember a peroxy acid, carbonyl OOH. Okay, one of the famous peroxy acids that's used is this one here. Okay, this kind of complicated one. Its name is metachlorobenzoic acid. Okay, real fancy name. So we often just abbreviate it MCPBA to keep it short. Okay. So some examples of making peroxy acids or epoxides. Okay, so anytime you see the use of MCPBA, puts the epoxide where the double bond was. Like that there. Okay. So we've already learned how to make these epoxides. What we want to do now is see how these things react. Okay? So remember that epoxides are cyclic ethers. Okay? So we already know some ether chemistry. Well, epoxides, their reactions are usually one of two. One type of reaction is what's called an acid catalysis reaction. And the other reaction is a base catalysis reaction. Okay. Let's go ahead and look at these two. And that's what we'll spend the rest of the lecture on. Okay? So let's first of all look at acid catalysis. So let's use H plus and H2O. How might you predict this to react here? We've got the lone pair on oxygen. So you might expect it to get that proton. Okay? Okay. So here we have a protonated epoxide. Well, we now have a very strong dipole moment toward the oxygen. Remember, oxygen with a positive charge is always what? Very extra electronegative. So it's going to make this delta plus very big. So now water can come into the picture. And where do you think water wants to react with? Okay? You might say the oxygen because it has a positive, but oxygen with a positive is never attacked because it would break its octet rule. Okay? So instead we'll come down here to this delta plus. And then that bond breaks, and those electrons go with the oxygen that's been pulling on them. So now the oxygen fully gets them. So the water has added on. Okay, so that bond is broken. Now you have oxygen with a positive and two hydrogens. So those hydrogens become acidic. So another water will come in and take one of them. And so we end up with this diol. That's a lot going on. Okay? We're going to do this a lot today, so it should become a habit by the time you're done. Okay, let's do another acid catalysis reaction. Let's see how far we can get on this one. Okay, so this time we have the epoxide on a ring. Again, the oxygen has two lone pair. So again, it'll attack the hydrogen, kick off the chlorine. get a protonated epoxide once again. What do you think the chlorine wants to do now? Attack where?
At the bottom.
Yeah.
At either carbon, okay? So remember, these carbons are delta plus. So the chlorine can attack either. Okay, so we'll just show it attacking the top one. That bond breaks. Those go with the oxygen. So oxygen has its 2 lone pair back, so it's happy. It's neutral. And so these 2 groups are now on the cyclohexane ring. Okay. Well, when you have 2 groups on a ring, what do you always have to show? Cis or trans. Okay. So, what do you think these 2 are going to be? They're going to end up being trans. Okay. So this always gives you the trans product. Okay. The question is why do those end up trans? Okay. Well, it has to do with this attack here, the chlorine coming in. Okay. How is that attack happening? Okay. Well, I really didn't draw this here with a fair view to you, okay? So if I were to redraw this more accurately, that oxygen is actually sticking up. It's not in the same plane, okay? So if that cyclohexane ring was this desk, that oxygen is sticking up like that, okay? So the chlorine, when it comes in, it's coming underneath on the opposite side of that oxygen. So that's why they end up trans to each other. Okay? So that's why you get the trans relationship. That ring is sticking straight up. It's not in the same plane as the cyclohexane. Okay. Let's do another acid catalysis, and let's see if you guys can figure this one out on your own. Okay. See if we can work out that problem. Anybody want to come up and give it a shot? Got a volunteer here.
Doesn't matter what I use.
Choose another method. Okay, very good. Good job. Okay, so this is the exact same mechanism as with water. Okay. So protonation of oxygen, and the methanol attacks, ring opens, and then just remove the acidic hydrogen, okay? For the sake of the camera, the final product that was drawn is this one here. Question?
Is there an importance in showing the last mechanism of the last hydrogen or just the final product more than that?
Yeah, if I asked for the mechanism, yeah, you'd have to remove that acidic hydrogen. Okay, so these are the three examples of acid catalysis that you want to know for opening the epoxide ring. Okay, not too bad. Now let's do the easier one. I saved the easier one for last. That's the base catalysis. Okay, so let's suppose we had our epoxide ring, okay? And now what we're going to do is react with base. So let's start off with a typical base, like OH minus, okay? So here, OH minus attacks, opens up the ring, So we get that there. And then the O minus takes a hydrogen. And we again get our diol. Okay, so you get the same product like we did with the acid catalysis in water, but just a different mechanism. Okay, so now that carbon will accept a nucleophile adding on. Okay, let's do another example. Let's see if we can draw the result of that reaction. Okay, it's the same exact thing. Again, both carbons are the same here, so it doesn't matter which carbon the OCH3 minus attacks. So we get our O minus as a leaving group, and then that will take a hydrogen from methanol now the two groups again end up trans, and the CH3O minus base gets regenerated so it can do another reaction if it wants to. Okay. So again, we got the same product as we did in the acid catalysis, but just a little different mechanism there. Any questions on that one? Okay, so again, always, these end up trans if they are on a ring. Okay. All right, well, we're going to do this again, but now we're going to add a little twist to the reaction. Okay. Say, what kind of twist are you going to add to the reaction? Well, the twist will be in the epoxide. This time I'm not going to start with both sides being the same. This time I'm going to make one side different by having an alkyl group there. Okay? And now, let's do same reaction here. Let's react with base and the alcohol. All right, so now since I have two different carbons, which carbon do you think will this attack the easiest? The less substituted, the least sterics, which will be this one here. Okay. All right, so let's draw the result of that. So there, the OCH3 is added, this bond is broken, so the O- will end up on the next carbon, which also has this ethyl group. Okay. Then lastly, that gets protonated with the methanol. So we get this one here. Okay, so this OCH3 ended up on the less substituted carbon. Okay, let's compare this reaction with now going back to an acid catalyzed reaction.
Constitutional isomers are okay, right?
Hmm?
Constitutional isomers are okay, right?
Yeah. Let's do the acid catalysis. We're now, I'll protonate first. Okay. So here, when we get to this point, something different's going to happen. Okay? Where here, the ring is going to open by way of an SN1 reaction, okay? And if the ring opens here on this side, I'm going to get a secondary carbocation. And then my methanol can add on. To review the lecture on the video. So now the methanol is adding on to the more substituted carbon because of the more substituted carbocation. You see, if it had opened this side, I'd get a primary carbocation, which is less stable. So that's why it opens on this side to give you secondary. And then remove our acidic hydrogen. To get that there. Okay, so this time it does make a difference if it's base catalyzed or acid catalyzed. Okay, if it's base catalyzed, the OHCH3 ended up on the less substituted. If it was acid catalyzed, it ended up on the more substituted. So that's where these things become a little tricky when I have an alkyl group on one side to make both sides different. Okay. Let's do one more example. Okay. We're going to look at another base catalyzed reaction. And this time, using the Grignard reagent. The Grignard reagent. Do you remember the Grignard reagent? And the Grignard is when I had MgBr on an alkyl group. Okay? So remember what happened when we had MgBr on there? In a sense, you could take it off. And this thing basically acts as a lone pair on that carbon. Okay, so I got another base catalyzed reaction. So this could attack either carbon, kick open the ring, there it goes. So the CH3 has added on that carbon. And secondly, H3O plus. Take one of the hydrogens. You get the alcohol. Okay? No, it's a lot of stuff. Hang in there. Why these videos are being made, so you can go back and review them. Okay, so let me give you one, see if you can do it. Okay, you don't have to draw the mechanism, just see if you can draw the product for that reaction. Anybody want to come up and try? Anybody brave out there? Chamonix. Okay. You can be the grand finale. Oh, it was ladies before gentlemen.
I always do it. I know
This
you
is
need
the
to-
grand finale, the last one of the class of the semester. You could have had your last fame on that tree.
You don't have to show a mechanism, say just final product.
Oh, final product?
Final product.
Oh.
Yeah, he just wanted to do that.
It's all right, you're allowed to make a mistake in the class.
Yeah, show they train.
Right. Very good. Everybody give him a hand.
Not yourself, come on.
class for himself, wow.
Oh, wow.
Look at that, pat on the back. Good job. Any questions on that?
Can you please exclude the mechanism of any text?
We got time in Monday. Today, not today.
We got a lot of other mechanisms besides this one.
One more day of chapter 11 and then
I was gonna get somebody else.
Okay. All right, so this is the end of the material for this exam, okay? Again, Wednesday, bring your textbooks and we will review for that exam.
Test on Wednesday.
Right.
Do we have a quiz today?